Welcome back, statistics. This is a continuation of the lesson on 12-1, the chi-squared goodness of fit test. Now, if you remember, the question we were trying to answer is, does the company that makes Skittles produce each color, whether it's orange, yellow, whatever, do they produce them with the same frequency? Okay, do they make the same number of green Skittles as they do yellow and orange and red and purple? Well, to test this claim or to test this hypothesis, what we did was we randomly selected 96 Skittles from the population of all Skittles produced. And I separated them into categories and I wrote down how many of each color Skittle that I had. And if you remember, those numbers are called the observed cell counts. Then, if the null hypothesis is true, if our initial assumption is true, if Skittles do, the different colors of Skittles do indeed occur with the same frequency, then our expected cell counts would be 19.2 for each one of those cells, okay? We would expect 20%, since there's 5 types of, or 5 colors of Skittles, we'd expect 20% of them to be green, 20% of them to be purple, etc. And 20% of 96 is 19.2. So that's how we arrive at the expected cell counts. Okay. Now, obviously, there is a difference between the observed cell counts and the expected cell counts. And of course, we can't get exactly 19.2 Skittles in any one of those categories because Skittles are indivisible, right? But do they vary enough? Is there enough total difference between the observed cell counts and the expected cell counts to lead us to believe that maybe the different colors of Skittles are not produced with the same frequency? Or is it just due to random chance? Now, if we'd have ended up with 95 green Skittles and 1 red Skittle, that would be some pretty strong evidence that Skittles are not produced with the same frequency. It would be very unlikely for us to end up with a sample of 95 green and 1 red if our initial assumption is true that the Skittles are produced with the same frequency. So, but is this enough evidence? Are the observed cell counts that we have, is that enough evidence to call into question or to cast doubt upon the claim that 20% of the Skittles are green, 20% of all Skittles are red, etc.? Well, to do that, we're going to go ahead and run a chi-squared goodness of fit test. Now, you've learned 2 test statistics so far this year. Everything okay with the camera?
Yes. You can keep talking.
Okay. T test statistic, which is used for, usually tests involving 1 or more means, either 1 mean or 2 means. And then Z, which is the test statistic that we use for proportions, tests involving proportions or intervals involving proportions. Well, we have to introduce a new test statistic here, and it is chi-squared. Okay, so the test statistic, remember the value of Z or the value of the value of Z or the value of T, you use that value to compute the p-value, okay, and then the p-value would tell you whether or not you were going to reject the null hypothesis. Well, the chi-squared test statistic looks like this. Okay, chi-squared is the sum for all cells, the observed minus the expected squared, all divided by the expected. Okay, so what we have to do, this is the formula for calculating the value of the chi-squared test statistic. Okay, let's look at, first of all, the sigma. I think we all know that means sum, in this case, the sum for all cells. We have 1, 2, 3, 4, 5 cells in our table. So when we calculate the value of chi-squared, it is going to have 5 terms in it, okay? Like for the first cell, for instance, what I do to get the term for the first cell is I take my observed cell count, 25, minus my expected cell count, 19.2. I I'd square that and then divide that by my expected cell count, again 19.2. Okay. Then for the second cell, okay, I take my observed minus expected divided by the expected. Okay, and I'd have to do that for all 5 cells to get the value of my chi-squared test statistic. That test statistic, and we'll talk about this a little bit later, is then used to find a p-value. And the p-value in a chi-squared test means really the same thing that it means in any other hypothesis test that we've done. It's the probability of obtaining a sample like this one or more extreme if the null hypothesis is true. Now, I'm not going to write out the rest of the terms here, but you have another one of these terms for this cell, one for this cell, and one for this cell. But I'm going to erase most of this now, and we're going to go ahead and do all the steps now for a chi-square goodness of fit test. So I'm going to erase this, and we will start with the null hypothesis. Okay. So we have some parameters of interest here. The parameter of interest, or the parameters of interest, are the proportions, okay, of each, in this case, color of Skittle. Eliza, do you mind closing that door? I don't know where that motor's coming from. I didn't say look out the door and observe. I said, you don't have to lock it. Yeah, thank you, Eliza. Well done. Okay, so for instance, the proportion of Skittles that are green, that's a parameter of interest. The proportion of Skittles that are red, that's a parameter of interest. So I actually have 5 parameters of interest here. So what I'll do is I'm not going to write out a definition of each parameter. We're just going to say that, for instance, pi sub r is the true proportion of Skittles that are red. Okay. Pi sub g is the true proportion of Skittles that are green, etc., etc. Now, once we've done that, and you don't have to write those all out, we're going to use context and, along with the subscripts just to infer the meaning, or infer the parameters of interest here. The null hypothesis, then, in this case, H naught, nice H. I'm going to put pi sub r. Hey, will you warn them not to walk in here? Tell them to come in the other door.
Go in the other door.
Go in the front door. In this case, pi sub r, null hypothesis is pi sub r equals pi sub g equals pi sub y equals pi sub p equals pi sub o. And I'm going to have to drop down one here. And they're all equal to 0.2. Now, the null hypothesis does not have to be a statement of that says that all of your parameters of interest are equal to each other. Okay, the null hypothesis, you could have a separate value for each one of. Thanks, Teddy. That's not the front door. You could have a separate value for each one of these parameters of interest. For example, if the company claimed that they made 30% red and 40% green, you could write pi sub r equals 0.3, pi sub g equals 0.4, or I may have gotten those backwards. If the company claimed that 10% of all Skittles were yellow, you could write pi sub y equals 0.10. But in this case, our null hypothesis is that the proportions are all the same. So that's why I set them all equal to 0.2. And then the alternative hypothesis is pretty easy here. It's simply H naught is not true. Hey, Teddy. Teddy.
What?
Will you go warn them not to walk through my video? Thank you, sweetheart. Love you. the alternative hypothesis is that at least one of the category proportions differs from the hypothesized value. Okay, you can simply write H naught is not true. Okay, now we are going to, I'm going to erase these hypothesis statements here, and we'll continue with the test here. Okay, now the checking the conditions, okay, or assumptions. Okay, these are the conditions needed in order to be able to run this test. One is we had a random sample. That's a single random sample from the parent population, the population of interest. And then the second the second condition has to do with sample size. Okay, and the way the sample size condition is met for a chi-squared goodness of fit test is this: all expected cell counts are greater than or equal to 5. Okay. If the sample's big enough to where every single expected cell count is at least 5, then our sample is large enough to run the chi-squared test. Chi-squared goodness of fit test, that is. Now, like with t-distributions, there are many of them, and their shape depends on the number of degrees of freedom. Okay? And before I draw what a chi-squared distribution looks like, let's talk about the degrees of freedom. So the degrees of freedom, DGF, is number of cells or categories. The number of cells, okay, which is the same as the number of categories. It's the number of categories minus 1. Okay, so for our chi-squared test, if you notice, we have 5 categories or 5 cells. So the degrees of freedom for our chi-squared test will be 5 minus 1, or 4. Okay. Now, if you looked at the way that the chi-squared test statistic was calculated, and I'm going to write it up here again because this is the time and the point in the test where we would calculate the value of chi-squared. And I'm going to tell you how to do it on a calculator. But if you look at how this is calculated, chi-squared is the sum of observed minus expected squared over expected. The numerator here, the larger the differences between the observed and the expected, the larger the numerators are going to be. Okay? And so the larger the differences between the observed and expected, the greater the value of chi-squared will be once I add up all those terms. Okay? So let's infer right away that the larger value of chi-squared leads to a greater probability of rejecting the null hypothesis, because that means that the observed cell counts are collectively farther away from the expected cell counts. Okay, now let's if you want to pause the video and get your TI-84, no, I don't mean you pause the video, Eliza.
I know.
Okay, so
I'm
I've got a
just making it
TI-84.
better.
Now, to run the chi-squared goodness of fit test, what we have to do is we have to put our data into the stat lists. So I'm going to go to stat, enter, and I'm going to clear out L1 and L2. And into L1, I'm going to put my observed cell counts. Okay, so I'm simply going to type 25, 14, 23, 20, and 14. Then in L2, I'm going to type my expected cell counts. Okay, 19.2, 19.2, 19.2, 19.2, and finally 19.2. Okay, so my data is where it needs to be in order to run the chi-squared goodness of fit test. Now, you find the goodness of fit test the same place you found all the other tests you've ever run in here. So I'm going to stat and then over to tests, and I'm scrolling down. And it's not letters, at least on my yellow calculator, it's not letter C, it's not just chi-squared test. It's the chi-squared GOF, or chi-squared goodness of fit test that you want. So it's letter D on mine. Okay, so I go in there, Notice mine is already in the default mode. It says observed is in L1, expected is in L2. I've got to change my degrees of freedom to 4. And then I'm going to go to calculate. Okay. And what I got was this. I got P, well, okay, let me write the chi-squared value first. I got chi-squared is 5.35 approximately, which gives me a p-value of 0.25, rounded to 2 decimal places. And, right away when you see a p-value like that, okay, you guys have been around the block a few times and you understand what p-values mean. And a p-value of 0.25, no matter what I chose as my alpha level or my significance level, I'm not going to reject that. Okay, if I used alpha equals 0.05, since p is greater than alpha, we fail to reject h naught at the 0.05 level. There is not sufficient evidence to conclude that the null hypothesis is not true. Okay, we didn't find sufficient evidence to, say for certain, that there's evidence that the category proportions are not the same. Okay. Now, a larger sample may have led to a different conclusion. We didn't have a very big sample in this case. Okay, so that's how you run the goodness fit test. Now, but hey, before we leave the calculator though, I want you to go back to that. Okay, go back to where you are, the screen where you set up the goodness of fit test. Only this time I'm going to change it from calculate to draw, and I'm waiting. It's not drawing it. My calculator. Okay, there it goes. Okay, so it is drawing a chi-squared distribution. I don't know. Can you see that, Eliza, on the screen?
Kind of.
Here, how's that?
Yeah, there we go.
Okay, yeah. So a chi-square distribution is shaped like that. They are skew right. Okay, every chi-square distribution is skew right, and the rejection region is always on the right-hand side. If you remember with Z or T distributions, sometimes the rejection region was on the left, sometimes it was on the right, sometimes it was on both sides. But with a chi-squared test, it's always the rejection region is on the upper tail. Okay. Every chi-squared distribution is shaped like that, skew right. Okay, you get a hump and then it goes out like that. Okay. How are we doing time-wise there, Eliza?
Almost 18 minutes.
Okay, yeah, we better sign off. So listen, this is getting ready to be Easter weekend. So tomorrow's Good Friday and such, and we have the day off. So if you guys want to take the day off, and do something else, with your family and such, that would be a good day to do it. Thanks for watching. If you have any questions, let me know. See you next time.